Hello students, welcome to Sciacademy. Hope you all are good and doing well. Students, during this bad time through which the world is passing through, we should be cautious enough for our health and should take precautions and should avoid the crowded place and maintaining the social distancing. But we should not stop the learning because if time went passes out, we can't recover it, we can't receive it. In the back. Previous video lecture, we have learnt about the important physical properties of light. Under this chapter number 9, ray optics and optical instruments. In today's video lecture, we will cover the next topics about the formation of images, sign convention, mirror equation, and so on. So, if you like this video, press the like button and share with your friends. And if you are watching for the first time, please subscribe the Sai Academy channel. So, students, let's start the video lecture. And I request you all to please stay tuned throughout all of the video so that you could not miss any important point which I maybe mention in the video lecture. So, under reflection of light by spherical mirrors, we are familiar with the laws of reflection, and under this, there are few concepts which we must revise before proceeding further. Here, in this figure, this is the angle of incident, and this is the angle of reflection. So, angle of incidence is the angle between the incident ray and normal to the surface of reflection, and this is the angle of reflection that made between the reflected ray and the normal. Also, the incident ray, reflected ray, and the normal to the reflecting surface at the point of incidence lie in the same plane. So all these three, incident ray, reflected ray, and normal, lie in the same plane. So this is the plane, and all these three lie in the same plane. Further, these laws are valid at each point on any reflecting surface, whether plane or curved. That means these laws are not only for the planes, true only for the plane surface. These are also true for the curved surface, curvilinear surface, spherical surface. In this chapter, we will be learning about the different optical phenomena. We will be talking about the special case of curved surface, that is the spherical surface, and in this case, normal is to be taken as a normal to the tangent to the surface at the point of incidence. That is, the normal is along the radius, the line joining the center of curvature of the mirror to the point of incidence. Before proceeding, we should must know about some important facts and definition. So, we will learn about the pole. What is pole? The geometric center of a spherical mirror is called the pole, and in the case of a spherical lens, it is known as the optical center. The line joining the pole and the center of curvature of the spherical mirror is known as the principal axis. Now we'll know about some sign convention to derive the relevant formulae. Reflection by the spherical mirrors and diffraction by the spherical lenses. According to this sign convention, all distances are measured from the pole of the mirror or the optical center of the lens. So here in this figure number 9.2, pole will be here in the case of the mirror and in the case of the spherical. we will use the optical center. The distances measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative. So all the direction in the along the incident light is positive, and opposite to this incident light is negative. The height measured upward with respect to the heights measured upwards with respect to the x-axis and normal to the principal axis of the mirror or lens are taken as positive, and the heights measured downwards are taken as negative. So basically, we are following the Cartesian sign convention. As you know that in Cartesian sign convention, if we are taking this as x-axis and as this as a y-axis, if we go if this side, it is taken as negative, and if you go this side, it is taken as positive, and upward from the x-axis are positive and downward from the x-axis is negative. Similarly, in the case of mirror or lens, we are adopting this sign convention that the direction of incident light is positive and opposite to the direction of incident light is negative, and upward the principal axis we are taking the positive heights, and downward to the principal axis we are taking the height as a negative. Further, we learned about the focal length of a spherical mirror. This is figure number 9.3, and this is the concave mirror. This is the concave mirror, and this is the convex mirror. In concave mirror, polish is done this side. In the convex mirror, polish is done this side. In the case of the reflection by the spherical mirror, we assume that the rays are paraxial. That means they are incident at the points close to the pole of the mirror, and they make small angles with the principal axis. So basically, what does it mean is that we are taking the rays very close to the principal axis, and that's why they will be making small angles with the principal axis. The reflected rays converge at a point. The reflected rays, if you are taking the parallel rays to the principal axis, they after reflection by the concave mirror will pass through the F on the principal axis of a concave mirror, and this F is called the focal point. In the case of a convex mirror, the reflected rays appear to diverge from a point on its principal axis. So in the case of concave mirror, you have seen that the parallel axis after reflection from this concave mirror reflected and passes through a point F on the principal axis, and this point F is called the focal point. But in the case of convex mirror, what happens is that these parallel rays after reflection from this convex mirror gets reflected, and they appear to coming out from the point F. If we are drawing these rays back side, that means if we are extending these rays, reflected rays backwards, they will appear to diverge from the point F on the principal axis, and this is also called the focal point, the principal focus of the mirror. Now we will talk about the focal plane. So, if the parallel paraxial beam of light were incident making some angle with the principal axis, the reflected rays would converge in case of concave mirror and appear to diverge in case of convex mirror from a point in a plane through F normal to the principal axis. This is called the focal plane of the mirror. You can see in the figure number 9.3c. Figure number 9.3c. This is the focal plane. So if any rays coming and incident on the concave mirror, then after reflection, they will be falling in a plane perpendicular to the principal axis and passing through this point F. This plane is called the focal plane. And this incident rays and reflected rays follow the laws of reflection. So these were the some definitions. Now we will derive the relationship between focal length and radius of curvature, that is F is equal to R by 2. So let's derive this relationship. For this, let us consider this figure 9.4a. In this figure, let C be the center of the curvature of the mirror, and let us consider a ray parallel to the principal axis striking the mirror at point M. Then the CM, this CM will be perpendicular to the mirror at M, and theta, this theta be the angle of incidence and this theta be the angle of reflection, and MD is the perpendicular from the point M to the principal axis. Then angle MCP is equal to theta and angle MFP is equal to 2 theta. So this MCP angle is theta and MFP angle is 2 theta. Students, I want to make you understand that this is the angle of incidence and this is the angle of reflection, and this is the normal at M. So by the law of reflection, this angle and this angle is equal, and if we have two parallel lines and a third line is intersecting these two lines in such a way that this angle theta must be equal to this angle theta. So we can see that this is the angle of incidence. Therefore, because of this principle, this is also becomes theta. Now we have angle theta and plus theta. That means this is 2 theta, and therefore again by this principle, this is this line and this line is parallel to each other, and a third line is intersecting these two lines. Therefore, this 2 theta is equal to this angle. That is, this angle becomes 2 theta. So students, I think you understand why it is becoming 2 theta and theta. From the triangle MCP and triangle MFP, we write tan theta is equal to md by cd and tan to 2 theta is equal to md by fd. Therefore, for small angle theta, as the rays are taken as a paraxial, so in that case we will take theta as a small, and for small theta, tan theta is almost equal to theta, and tan to theta 2 theta is equal to 2 theta. Therefore, we will take MD by FD is equal to 2MD by CD. That is, FD is equal to CD by 2. This FD is equal to CD by 2. Now, for small theta, the point D is very close to the point P. These 2 points D and P will be very close, almost overlapping on each other for the small theta. Therefore, in that case, we will take FD is equal to FP. In that case, FD will be equal to FP, and that will be equal to focal length. And CD will be equal to Cp, and that will be equal to radius of curvature. Therefore, you can write that F is equal to radius of curvature by 2. So this is the relationship between the focal length and radius of curvature. That is, focal length is always equal to the half of the radius of the curvature in case of the reflection from a concave mirror or a convex mirror. Similarly, we can derive the same formula F is equal to R by 2 from this figure also. Now, let us derive the mirror equation. 1 by F is equal to 1 by V plus 1 by U. This is known as the mirror equation. We will derive. For this, let us consider this figure number 9.5. Before deriving this mirror equation, let us understand the definition of real image and the virtual image. So, students, if rays emanating from a point actually meet at another point after reflection and or refraction, that point is called the image of the first point. And the image is real if the rays actually converge to the point, and it is virtual if the rays do not actually meet but appear to diverge from the point when produced backwards. Thus, an image is a point-to-point correspondence with the object established through reflection and or refraction. To make a image from an object, in practice, we choose any two of the following rays. So we will take any two of these four. What are these? First, the rays from the point which is parallel to the principal axis, that is this rays. The reflected rays goes through the focus of the mirror. Second, the rays passing through the center of curvature of a concave mirror or appear to pass through it for a convex mirror. The reflected rays simply retraces the path. So second ray we can take is the rays, this rays passing through the center of curvature. And in this case, rays after reflection simply retraces its path. So if we are taking this ray and this ray, we can form the image. And third we can choose is the ray passing through are directed towards the focus of the concave mirror. The reflected rays is parallel to the principal axis. That means if the ray pass through the focus, the reflected ray is parallel to the principal axis. That means if we are taking this ray, then after reflection, it becomes parallel to the principal axis. Now fourth ray which we can take is the ray incident at any angle at the pole. In this case, the reflected rays follow the laws of reflection. If this ray is falling at the point P, that is the pole of the mirror, then it follows after reflection the laws of reflection and it comes in this way. So, any of these four rays we can any of these four rays we can take to construct a image. Let us move further proving the for deriving the mirror equation. For this, let us consider an object AB is placed in front of a concave mirror, this concave mirror, and an inverted image is formed A B prime A prime. That means this this image is real as the parallel paraxial rays after reflection from the mirror passing through the focus and another ray passing through the center of curvature meet at point A prime and form the image. Therefore, this is the real image. Actually, these are not only two, three rays which form the image. For convenience, we are taking only two, three rays, but in actual case, an infinite number of rays emanate from any source in all directions. Thus, point A prime is image point of A if every ray originating at point A and falling on the concave mirror after reflection passing through the point A prime. Now, from the figure, two right-angled triangles A prime, B prime, F and MPF are similar. Therefore, B prime A prime by PM is equal to B prime F by FP. Since PM is equal to AB, which is equal to the length of object, therefore we can write B prime A prime divided by BA is equal to B prime F by FP. Since angle APB is equal to A prime B A prime P B prime, the right angle triangles A prime B prime P and ABP are also similar. Therefore, from this case, we can write B prime A prime divided by BA is equal to B prime P divided by BP. Comparing equation 9.4 and 9.5, we can write B prime F divided by FP is equal to B prime P minus Fp divided by Fp is equal to B prime P divided by Bp. Now, equation 9.6 is a relation involving magnitude of the distances. Now, now apply the sign convention. Since we note that light travels from object to the mirror MPN, hence this is taken as the positive direction. And to reach the object AB, image A prime B prime as well as the focus F from the pole P, we have to travel opposite to the direction of the incident light. Therefore, we'll take all these three as a negative. So B prime P is equal to minus B, FP is equal to minus F, and BP is equal to minus U. So substituting these values with sign, we get minus V plus F divided by minus F is equal to minus V divided by minus U, which is equal to minus V minus F divided by minus F is equal to V by U, which is equal to V minus F by F is equal to V by U. Therefore, V by F is equal to 1 plus V by U. Dividing both sides by V, we get 1 by V plus 1 by U is equal to 1 by F. This equation is known as the mirror equation, which we wanted to derive. Now, we can define the linear magnification as the ratio of the height of the image to the height of the object. That is, linear magnification can be given by m is equal to h prime by h. So, linear magnification from the figure is b prime a prime divided by ab. Applying the sign convention, we can write that b prime a prime divided by ba is equal to b prime p divided by bp. So, minus h prime by h is equal to minus b by u. As h prime is below the principal axis, as we are taking minus sign, and AB is above the axis, so we are taking positive H. And since V and U both are in the opposite to the incident light, therefore we are taking both as a negative sign. After reduction, it becomes M is equal to H prime by H is equal to minus V by U. Now for the case of real inverted image found by concave mirror, we have derived the mirror equation as well as the magnification formula. With the proper use of sign convention, these are valid for all the cases of reflection by spherical mirror, whether it is convex or concave. So students, these are the things for now. Hope you understand all these things. If you have any doubts, you can put your query through comments. You can also follow us on Instagram page, Telegram page, and you can also put their queries, doubts on the social media platform. Students, if you like this video, please share it with your friends and press the like button. And if you are watching for the first time, please subscribe this channel. Sciacademy. Thank you.